The warm-up question for today says a plane at constant velocity drops a relief package. Where does it land? We're going to assume that there is no air resistance in this question. And so we've got three choices labeled here at the bottom of the picture, A, B, and C. And what you need to remember whenever you're looking at a question like this, which you will see this again, I'm telling you right now, it's going to be something that you see probably on your test, but it's a question that's been on the TEKS test in the past as well. But you need to keep in mind that if this plane is moving while holding this box, that this box is also moving. So let's say they're both moving, 300 kilometers per hour. Okay, then that means this is also moving 300 kilometers per hour, and they're both moving at that same speed. And so when the plane drops the box, okay, the box is also moving at that same speed. And in the horizontal direction, there are no forces acting on the box. The only force acting on it will be the force of gravity. And so this box is going to keep moving forward at that same rate. The plane is going to keep moving forward at that same rate. They're going to keep pace with each other. Now, if there was air resistance in the real world, if this happened, no, it's not going to land directly underneath the plane like it does here. The answer you should be selecting is B. But without air resistance in this ideal condition, yes, it's going to do this because, and let me illustrate it further here. Okay, because again, the plane is moving forward, the box is moving forward, and I've lined them up better on this one. So each second that passes, both of them are moving the same amount forward. It's just that the box happens to also move downward once it's been released. Here's an animation that shows the same thing. You can see the red dot here representing, the package, and they start out together. And as it drops, their horizontal motion keeps pace because remember, a projectile has constant horizontal velocity. And if the plane continues flying at the same rate, it also has constant horizontal velocity. They're going to keep up with each other. And so when the package lands, it will be directly underneath the plane at that point in time. Which is what you see in this animation. It's what's represented by point B as well. So please make sure that you've answered the warm-up question. Again, you should be selecting letter B. So today we're going to take some notes on projectiles that have been launched at an angle. But before we get into that, I want to go all the way back to the free fall unit and talk about objects thrown up in the air. Because if you have a projectile launched at an angle, it is something that has been thrown upward and forward, but thrown upward. And so we need to remember some of the basic rules that we talked about in the second unit of the year when we talked about objects in free fall that were launched upward. This problem is from the notes in Unit 2, and it says a ball is thrown upward at 3.4 meters per second from the ground. What will be the maximum height that it reaches? And when we look at this question, it doesn't appear that we're given very much information. We know that we have this initial velocity of 3.4 meters per second upward, but that's the only number in the question. And so you have to start thinking, what else do I know about this scenario? And I know that this is going to be an object in free fall, so I know my acceleration. I can start there, and I can say the acceleration is going to be negative 9.8 meters per second squared because gravity is going to pull it down. So although I throw it upward, it's going to slow down. It's going to reach this highest point where it's going to stop for just an instant, and then it's going to fall back down again. And again, y'all know this from just real world. Okay, but what else do I know? Because those two pieces of information aren't enough to solve a problem. And the other things that I know are about this point up here at the top. I know that at the very top it has to stop for an instant. I said it just a minute ago. And so if I choose this point at the top to analyze, I can say that the final velocity at the top is 0 meters per second. And you can label it VF. You can label it VTOP. Whatever you need to do to make sure that you understand that we're focusing on this point. Okay, and so if I want to determine the height, I can do that because I can solve for delta x, or really delta y since we're in the vertical, but I can solve for my displacement vertically with this information, VI, A, VF, delta x. And if I look back at my kinematic equations from last semester and the ones that we've been using for the last couple of days, I see these variables show up in one of these four equations, and if you take a look, you'll see it too. The one that's going to be easiest for us to use that we can do in a single step is going to be equation B. Vf squared equals Vi squared plus 2 times A times delta X. Now, could I find time first and then delta X? Absolutely. You're welcome to do that. It's an extra step, but there's nothing wrong with doing it that way. But I'm going to go ahead and do it this way. Vf is 0. So I'm going to substitute 0 squared equals Vi is 3.4, so 3.4 squared plus 2 times negative 9.8 times delta X. If I go ahead and solve this, this number right here, this 3.4 squared, becomes 11.56, and I've gone ahead and subtracted it to the other side. 0 minus 11.56 is, of course, negative 11.56, and then 2 times negative 9.8 is negative 19.6 times delta X. Again, if I want to solve for delta X, I'm going to divide both sides by this negative 19.6. 11.56 divided by negative 19.6 is 0.59 meters, and therefore the displacement of this ball, or the maximum height, again, to this top point where the velocity is 0, this would be my displacement, and therefore this would be the maximum height that it reaches, 0.59 meters. Okay, so when you're doing one of these problems where something is thrown upward, you know something about this maximum position. You know that the vertical velocity at this point is 0, and you can use that to solve problems like this. Okay, let's answer this question. Same scenario, but now we're asking instead, how long is the ball in the air? You'll notice that I relabeled everything, including the displacement that I found, because that is now a piece of information that I'm able to use. And so I can go ahead and solve for time. Now keep in mind, when I solve for time, I'm only solving for the time it takes for this ball to get up to this point, because this is the final point that I chose. So this is not going to be the total time in the air, it's only going to be the time up to the top. So I have to take care of that at the end. But let's go ahead and solve for it. Again, I'm trying to solve for time. I can actually use any of these equations that contain time. That's going to be A, C, or D. All of those will work. I'm going to go ahead and use the first one because I think it's the easiest. But if you use one of the other ones, there's nothing wrong with that because you have all of those pieces of information. Substituting in, I have 0 equals 3.4 plus negative 9.8 times t. If I subtract that 3.4 from both sides, I have this, negative 3.4 equals negative 9.8t, and then I'm going to divide both sides by negative 9.8 to get a time up of 0.347 seconds. Again, this is just the time to go up to this top point. That's not what the question asked. It wants to know the total time in the air. And one of the rules you need to remember when we're dealing with a projectile thrown upward is that time up equals time down. So long as your projectile is returning to the same height, everything's going to be symmetric. You're going to have the same amount of time to get up and the same amount of time to get down because you have the same displacement up as you have down. And so I'm just going to double this number. That's going to give me a total time in the air of 0.694 seconds, and that is the answer to this question. You also need to remember those graphs that we did. You're going to see these again too. It says to sketch the xt, vt, and at graphs for this scenario. Again, for my xt graph, I need to start out with an upward motion that's going to slow down. Okay, and then it needs to turn around and speed up in the other direction. It's going to look like this. You're going to get a parabola. So you're going to start out with a steeper slope. It's going to flatten out as it slows down. Your maximum height's going to be right here, and then it's going to continue, but it's going to fall now. My slope becomes negative, and it gets steeper and steeper as it speeds up as it falls. For my VT graph, I need to start in the positive direction because it's thrown upward. So I'm going to start in the positive region of my graph. And I'm going to draw a line that crosses the x-axis because remember, if it gets to the x-axis, the velocity is 0. If I look at this, my velocity is 0 up here at the top. So I'm going to go from having a positive velocity to 0 velocity to a negative velocity. And it needs to be a straight line because it's a constant rate of change. Why is it changing? It's changing because of gravity. It's a constant change of negative 9.8 meters per second squared. So the slope of this line would be negative 9.8 if I had numbers here. And that's what's going to show up on my AT graph, is that negative 9.8. It's a constant acceleration, so it's a straight horizontal line in the negative region of my graph. Again, if I had numbers, this would be at negative 9.8. This is what the vertical graph is going to look like for any projectile, okay, thrown upward, okay, or up at an angle. The vertical piece is still going to look like this. Okay, so let's take a look at some questions just to make sure we're remembering all of these things about these vertically launched projectiles so that we can then talk about ones that are launched not just vertically but also forward. Okay, this one says a ball is thrown straight up from the ground. Labeled positions are shown at each second. Identify the direction of the acceleration and velocity at each point. Well, at points A, B, C, D, and E, my projectile is moving upward, so the direction of my velocity in those first 5 points is positive or up for the velocity because I'm moving that way. At point F, my velocity would be 0 because it says this was thrown straight up. I know it looks like it's been thrown up and forward, but they just did that so you could see the points more clearly. At point F, you wouldn't have any velocity. It would stop moving for that split second before it falls back down. For points G through K, my velocity is negative. It's downward because the object is falling. So you're going to have positive velocities for the first half. You're going to have negative velocities for the second half. However, when you look at the acceleration is the same the whole time. The acceleration is negative 9.8 meters per second squared because we are dealing with free fall. We're dealing with acceleration due to gravity. The next question says, where is the ball moving fastest? And that's going to be the point where it has been just launched. That's A, it's just off the ground. It was just launched upward or thrown or whatever. And at point K. When it returns to the same height, it will be moving the same speed. It will be moving the opposite direction, but the speed will be the same. So the answer to that second question would be point A and point K. The last question says, how does the speed of the ball compare at points D and H? And again, same thing. Because point D and point H are at the same height, they're going to be moving at the same speed. They're going to be moving opposite directions, of course. D is up, H is down, but the speeds will be the same if you're at the same height. Okay, so what if it's launched at an angle? We were just dealing with something thrown straight upward, but what if instead of just up, it's also forward like this football? And this means that there is an initial velocity in both the horizontal and vertical directions. Remember, horizontal motion is independent of vertical motion, but taken together you get this curved parabolic pathway. And you can see my velocity vectors, I've labeled them on this image. It's moving forward the whole time. It starts out moving up, it gets a little slower, it's no longer moving up here, and now it starts to fall back down. Okay, and so you have velocities in both directions, with the exception of this maximum height at the apex. It's just horizontal there because you have 0 vertical motion. So again, what if we graph it? Well, the vertical motion graph is going to look just like it did for free fall. You're going to have an object moving upward that slows down to a stop for that brief moment before turning around and speeding up in the opposite direction. And so your graph is going to look something like this. For your VT graph, again, it's going to look exactly the same as it did for free fall, for an object thrown straight up, because all we're looking is the vertical piece. And it's the same whether it's launched forward or not because my vertical motion is independent of my horizontal. And so I'm going to start out with a positive vertical velocity. It's going to slow down to 0, and this point right here is going to be at max height. There's no vertical velocity here. It's just horizontal, but I'm not graphing that yet. Okay, and then it's going to continue, but it's going to be falling. So I have negative velocities here, and again, you can see those negative vectors here. Acceleration, again, due to gravity. Gravity is a constant rate of negative 9.8 meters per second. So these graphs look exactly the same as they did in free fall. That's why I wanted to start there. However, we do also have horizontal motion. With the free fall object thrown straight up, we didn't have any of these graphs because there wasn't any motion. But horizontally, we have constant velocity, just like we did yesterday. In this example, it's 10 meters per second the entire time. If I want to show that on an XT graph, that I have a forward positive velocity of 10 meters per second and that it's a constant velocity, I need a straight line with a positive slope. My velocity time graph, I'm going to have a horizontal line because my velocity is 10 and it's still 10 and it's still 10 the entire time. Positive 10. Acceleration, 0. There is no horizontal acceleration. Okay, and so that's what your horizontal graphs are going to look like for a projectile. This looks like any constant velocity graph that we learned in Unit 1. Okay, if we're just looking at the horizontal piece. So again, just to recap some of this, if a projectile is launched on level ground and it's launched upward at an angle like this, time up will equal time down, just like it did for free fall. VI and VF are going to have the same magnitude. If it's launched upward at, let's say, positive 20 meters per second, then at this point over here, it will be negative 20. So maybe positive 20, positive 10, 0, negative 10, negative 20. Okay, and so you're going to have equal and opposite velocities at that point. And at this point, by the way, they'll be equal and opposite as well. Maximum height, this point right here, is at half of the total air time. Because time up equals time down, this would be time up to this point. And then, of course, from this point here is time down. Let's try an example calculation. It says James punts a 0.8 kilogram football. It has a hang time of 2.1 seconds and lands 51 meters down the field. With what speed did he kick the football? And I have a little drawing up here already to show the trajectory of this football, and I've got just some random things labeled. I know, like we just talked about, that whatever my initial velocity is here, at least vertically, my final velocity here will be equal and opposite, and I labeled the max height because there's some stuff I know about that point too. So let's go ahead and see if we can label some things. I know the time, hang time 2.1 seconds. That means the total time to get from this point where it's been kicked to this point where it lands. That's your total time. I know that my horizontal displacement is 51 meters because it lands 51 meters down the field. I know that vertically, if I choose this first point and this last point, which is what I'm going to do, I'm going to choose the point to impact. Then my vertical displacement is 0 because I started and landed at the same position. I know that acceleration in the vertical direction will be due to gravity, negative 9.8 meters per second squared, and that horizontally I will not have any acceleration. And that looks like all of the information I have been given in the question. They didn't give me any velocities. Okay, so we're going to start by trying to figure out what the horizontal velocities are. Because if I want to answer this question, with what speed did he kick the football? I know he kicked it diagonally. I know he kicked it both up and forward. The question isn't asking with what horizontal speed, it's not asking with what vertical speed, it just wants to know the total speed. So I need to find both the horizontal and vertical initial velocities so that I can figure out what the resultant, what the total would be by vector addition. So let's start by solving for my horizontal. Okay, I know that I have constant velocity here. And when I have constant velocity, I can use this equation. My displacement is equal to my velocity times my time. This is basically the fourth equation on that list of kinematic equations. Delta x equals VI plus VF divided by 2. That's your average velocity times t. But since the velocity is the same, it's just the velocity. There is no average here. Whenever you're horizontal, it's the same the whole time. So I can substitute into this equation, plugging in my displacement, 51, equals V times my time, 2.1, divide both sides by 2.1, and I get a velocity of 24.3 meters per second. And since that's the horizontal velocity, it's the same the whole time. It doesn't change. That's what this means. 0 meter per second squared acceleration means it's not going to change. So I can fill it into both of those boxes. So we found the horizontal piece, but again, the question doesn't say what's the horizontal speed. It wants the total. We kicked it diagonally. We need to get the vertical as well. So let's go ahead and solve for our initial vertical velocity. Again, I can solve for that because I know time, I know acceleration, and I know delta y. I can use this kinematic equation to solve for VI. Delta y, again on the board it says delta x, but again it's your displacement in the y direction, so we typically use this symbol instead. Delta y equals vi in the y direction times t plus 1/2 at squared. Again, as a reminder, if you're solving for something vertical, you only get to use the vertical side of the table. Over here, when we solve for horizontal, we only used the horizontal side of the table. So if I'm going to substitute in, I can only use these values in blue. Delta y was 0. It equals vi times 2.1 plus 1/2 times negative 9.8 times 2.1 squared. This whole piece over here, half of negative 9.8 is negative 4.9, and if I multiply that by 2.1 squared, I get this, negative 21.609, and so now I have this right here. If I want to solve for vi, I got to get it by itself. Okay, right now it's being multiplied by something, but then there's also a subtraction step. Your first step algebraically is to move this. Please don't try to subtract these. They are not like terms. Your next step is adding 21.609 to both sides. That cancels it here, it moves it here, and now we have this. 21.609 equals vi times 2.1. My last step is going to be dividing both sides by 2.1 to get my initial velocity of 10.29 meters per second. So when he kicks the football, he kicks it with both a vertical and horizontal velocity. He has 10.29 meters per second of vertical velocity and 24.3 meters per second horizontal velocity. But again, the question doesn't want to know that. Oh, by the way, you'll notice I also filled this in. Okay, the final velocity at this last point, equal and opposite to what we started with. So if we start with 10.29, it ends at negative 10.29. Again, that's if I'm going from the first point to the last point. You can also analyze this point. I didn't do that, but you could have. All right, so I'm going to, from here, we have to actually finish the question. Again, when the ball's kicked, we have both of these velocities, up and forward. But if I want to answer my question with what speed did he kick the football, I need to add those together by vector addition. And by vector addition means I add them head to tail. So I add them where I make a right triangle. Here's my horizontal, here's my vertical, here is my hypotenuse, my diagonal speed that he kicked it with. If you want to solve for the hypotenuse of a right triangle and you know the lengths of the two legs, you are going to use Pythagorean theorem. A squared plus b squared equals c squared. So that's going to be 24.3 squared plus 10.29 squared equals c squared. C squared will therefore equal 695.68. Take the square root of that and you get your answer. The velocity, that diagonal velocity, is 26.4 meters per second. For an L class, you would stop here. Actually, for both you would, because it just says with what speed. But for the K classes, remember, you would also need to then find an angle if the question asks for velocity instead. So I'm going to label it up here. Okay, so that's how we solved this one. Now, I told you a moment ago that I could have instead analyzed my data to this point. Had I done that, I would have said my final velocity was 0, but I also would have used a value of half the amount of time. But I could have solved for my initial velocity from that information here. Okay, and that's what I made a note of. You can also solve this using the max height or apex vertical data. When you do this, you have to use half the time, and your final velocity in the y direction is 0. Now, if you're comfortable with the way that I already did it, then do it that way. But if your question was asking you not just the speed, but also the max height, if they wanted you to find the max height, you would need to use this data. So sometimes this is a better option for you depending on what you're being asked for. For what we were asked for, it didn't really matter which way I went about doing that. Okay, but you would get the same answer, that 10.29, and then you would finish the question the same way. Okay, so I've filled in everything. I didn't fill this in because I didn't solve for it, but I filled in everything else. And you can do this. You can make a table and add an extra column. Just make sure that you label your vertical columns so you know this one's to impact, this one's to max height. The question I have up here now, the follow-up, says find the kinetic energy of the ball at max height. And so what do I know about the ball at max height? At this point that I labeled here with an X, I know that the ball is moving horizontally. I know it's not moving vertically, and so the velocity that it has is all horizontal. And so if I wanted to find the kinetic energy, that kinetic energy equation requires me to use a velocity. Well, I would need to use my horizontal velocity because I don't have any vertical velocity up here. If I had both, I would need to get the resultant, use Pythagorean theorem, all that. But I just get to use this one because that's the velocity at the top, 24.3. There is no vertical. And so I would need to solve for it using just that 24.3 meters per second plugged into my KE equation. KE equals 1/2 mv squared. The m is in the question, the mass 0.8 times that 24.3 squared, and I get 235.92 joules. What is the work done by gravity on the ball as it rises to its max height? Now I did go ahead, actually I don't have it up here right now. There are two different ways that you can solve this. You can find the change in kinetic energy because you know the velocity that we started with and you know the kinetic energy up here already. So you could find the initial kinetic energy, you'd have this final kinetic energy, you could find the difference, that would give you net work. Or you can multiply the force acting on the ball by the displacement of the ball. The force is going to be gravity. The displacement, again, we only care about force and displacement when they're parallel to each other, so we'd be looking for the max height here. So in order for me to use the second one, I would need to solve for max height. The first one, I would just need to use the velocities that I already had. And since I already have the velocities, I'm going to go ahead and do it this way. My final kinetic energy is 235.92. We found that a minute ago. That's at max height. My initial kinetic energy would be 1/2 times mass times that initial velocity that we found. That's the hypotenuse of my triangle we found a minute ago, 26.4 squared, and that would be this value. And so now I can just find the change. I go from having a KE of 278.27 to losing some energy so that it's only 235.92. And so I could find the change by subtraction. And I would get that the work done is negative 42.35 joules. And what's doing that work? What force is acting on this ball to cause it to lose energy? Gravity. It's the force of gravity slowing it down as it rises to that maximum height. So again, it says it in the question, what's the work done by gravity? Okay, again, this is the other way you can go about doing it, is by using this equation, force times displacement. And that force will be force of gravity. You would need to have the max height first, though, in order to use this. Okay, I could find that really quickly with this equation. Substituting in VI times T plus 1/2 AT squared. Again, if you're using this data to max height, notice my time is half. Don't use the whole time because the time to max height is only half. Okay, my maximum height is 5.402 meters. And so I can plug that into my table, and now I know how much distance is covered, what's the displacement as it rises up, and I can multiply that by the force of gravity. Okay, force of gravity, as a reminder, is mass times acceleration due to gravity. My mass is 0.8, my acceleration due to gravity is negative 9.8. That makes my force of gravity negative 7.84. If I multiply that by the height that it rises to, I get a work of exactly the same thing we found a second ago, negative 42.35 joules. All right, so this assignment, 702.3 mixed projectile motion problem set, is going to be your assignment for tonight. It is not due tonight. This is actually due next week on Tuesday. And this notes are also for Tuesday, so I apologize for the screen being a little off. But this is your assignment for class today. You can get started on it. It is not due tonight. It is due on Tuesday of next week.